let's start recording and let's get started. So I'm very excited. This is a very fun set of slides. We're finally going to learn how to make our own functions. It's been so long. We've been using other people's functions. It's time, right? So there's a lot to learn about. It's going to take a few lectures to get through, but oh man, is it worth learning about. So lots of stuff to learn. So let us begin because, I don't really have to motivate this to you, most likely. You've probably noticed that, okay, I've been writing these giant main functions, haven't I? It's like int main, parenthesis, parenthesis. I must have muted the wrong sound. Sorry. There we go. Int main, parenthesis, parenthesis, curly brace, return 0 way down here at the very bottom. But you've been doing all this stuff, like some stuff over here, some stuff over here, some more stuff down here. All we know how to do is write a giant main function to do everything that we want to do. But really, some of these pieces, like this is a separate idea, this is a separate thought, this is a separate thought, this is a third thought, or maybe some things are being repeated. Wouldn't it be nice to make this main function 3 lines long and put all those giant chunks of code into their own functions? That's the goal. That's where I'd like to take us. All right, so let's make our own function so that inside of main, we don't have to do a million things. We can send off the million things to somebody else. We can have main call some function that we make for ourselves, call it F1, and then F1 maybe it has 2 things that it needs to do. It needs to complete task F2, make a function that calls that, and then it can complete task F3. We'll make a function and it'll just call it, and maybe F3 needs some extra help. And it'll call a little helper function F4 that we also make. So that's kind of the game. We're going to make functions, and they'll call other functions, and it just all works out. All right. So you actually know how to make a function. You've been making one this whole time, right? You've made main. Main is a function definition. This generalizes. So let's talk about it. All right. So here's the skeleton of how you make a function. The very first thing you give is what's called the return type. You say int. Because main returns an int. It returns a 0 at the end, right? So that's the return type. I'll label these with numbers. Like this is number 1. Label number 1. That's the return type. You say the type of thing that's going to be given back by your function. And then, of course, you give it its name. Like, all right, this one's called main. Don't really have much choice in the matter for that one. But every other function that you make can have whatever name you want. And then, so that's number 2. And then you have things that your function takes. So it's going to take arguments when you call it, and when you define the function, those arguments are going to be passed to these things called the parameters. All right, so in between some braces, you give parameters if there are any. Sometimes we make main functions without any parameters. All right, so those are parameters. And then, of course, you have what you want to have happen when the function gets called. It's the body of the function. So that's like number 4. And then finally, if your function has promised to give back something of some type, you have to have a return statement to actually do that giving back. So return gives back a value to whoever called you. And so as far as main is concerned, it's like the terminal who's calling you. But when you're making your own functions, like maybe you call that function from main, and it needs to come back to main and give back a value. Like you call square root, it needs to return a value back to main, give you back that square root that you're asking for, right? So that's what it looks like. You've been doing it this whole time. Do these pieces make enough sense? Are we ready to make our own? We'll make a very simple function first, I think. That'll get us ready. So that's how you do it, though. Let's make a function to add together 2 integers. All right? And so naturally, it's going to look like this. We'll call it add. It will give back the sum of 2 integers, so the return type is still an integer. And then it takes 2 things. We need to have space, 2 parameters that will get replaced with things when we call it. So that's what it's going to look like. Int add, int x, int y. And these are just variables. You can give them any name. Doesn't matter. And then you just start giving it a body and say what you want to have happen when you get those x and y's and somebody called you. All right? So you're taking 2 ints and you're going to give back their sum with returning. Okay? So let's make this. And let me show you how you call it. And it will all hopefully make sense. So make a file called functions.cdp. All right, so I would like a function that works like this, like cout add 4, 5. It's very simple. It's just going to add two numbers. But let's make this function that's called add. So, all right. It's called add. It's going to give back the sum of two numbers. So the sum of two ints is still an int. And then it takes two ints as parameters. So int x, we'll say int y. Those can be their names. And then now, here in the body of this function, I need to, well, I've been given x and y. I need to do something with them. So my job is to give back the answer, give back their sum. That's my simple example. So give back, and that means return in this new statement, right? That is return the sum of x and y. That's what our simple add function is going to do. Right? So I'm going to return the result of adding x and y. So like do this first, and return back the answer to whoever called you. All right? So that's what's going to happen. That's what it looks like. And here I am calling that function I just made. G++ functions, dash o functions. Woo, and I get my 9. Awesome. So what's happening is I said x and y here, but I passed along 4 and 5 here. Essentially, when you call a function, like you say it here, it's going to take the 4 and pass it along into the x. It's going to take the 5, pass it along into the y, and then start running all this code. That's pretty much what it means to call a function. So, like I said this, I said add with two values, maybe a and b, somewhere in main. And what that means is it's asking you to like jump up to the body of that function, start running its code with x set to the first thing and y set to the second thing. So run the body of that function, of the add function, with the x parameter set to a, because that was the first one, and the y parameter set to b. That was the second one, just in order. The a thing, the first thing is going into x, the second thing is going into y, and then we start running all that code. And it's going to give back an answer. And then suddenly we have that back, and we can print the 9. Okay? Are there any questions about that? So that's beautiful. We've like abstracted away what it means to add something, even though we could have just used plus. This will get more complicated soon. But the magic of functions is you write this code once, and then you have this functionality forever that you can reuse. So I can call add again, pass along like 1 and 7, and that'll make 8. It'll jump up to this code and set x to 1 and y to 7 this time, the second time it's run. See that? The whole point of making functions is so you can reuse them, do the same thing again, with different values, different parameters, different arguments. All right? That's the goal there. We're good with that? It's the whole reason we write a function, so we can call it multiple times. Otherwise, we could have just put it in main. All right. There's the concept of overloading functions. So like this was an add function that took two ints and gave back their sum, which was another int. We could make another add function that takes two doubles and gives back their sum, which will be another double. Or it takes two strings and adds them together, which will make a bigger string, right? So let's do that. Let's overload the add function. Let's make some different versions of it. Let's be like, all right, instead of this one, this is looking a bit repetitive. There's a way to solve this, but you'll have to wait till CSCI 41. Double add, double x, double y. Why not? So, same function. Now it works on doubles. Now if I call add with doubles, it knows what to do. All right? Same with like strings. If I include the string library. Whee! So, I got some strings. Maybe if I pass along a string x and a string y, I can still use the plus on strings. I'll jumble them together, make a bigger string. And of course, we're not giving back a double at that point. We're giving back another string. All right, so it's just the same body, but different parameter types and different return types. And C++ will know which one to call based on the types that you give. So like, if I do this, if I say cout the add call to 3.14 and like 5.67, it's going to know to go to the double version of add. Be like, all right, you gave me double parameters. I see what you wanted to call this one. I get it. All right, that's going to work there. And then same for strings. It's like I make a string s1, like that's high space, and then I don't know, s2 can be mom exclamation point. Then I can see out adding those. Add s1 and s2. That'll definitely hit my add function that took strings, right? It's like, those things weren't ints or doubles. You must have wanted to call this one. All right, I see. I'll give you back a new string. That's what's what's going on there. And yeah, that's the whole idea. So here is this running. It should have the output that you expect to see. And here are like the definitions up here. We have different kinds of add. Just always taking two things, giving back their sum. Okay? Any questions about any of that? We just made functions. We did it. Those are functions that give back things. Okay? So that's the first kind of function. They're returning something back, so they can, like, this is getting replaced. It can be used in a larger context. I can multiply its result by 2. We've done that with, like, square root, abs, all that fun stuff. So that's that one. Let's do something completely different now. Let's write a function that just prints something. Print hello to the screen, okay? So this function is meant to be called, like, we're going to give it this name. It's meant to be called on a line by itself, right? Just like srand. It doesn't, like, it just does something for us. We don't like add 2 to the result of srand. We just use it to initialize our random number generator. Print hello. We're just going to call it on a line by itself. It doesn't need to give anything back. Like, there's no point to that. It's just like, you call this, it's going to print hello, right? So there's a special type for functions that aren't meant to give back anything. For a function that doesn't return anything, it just goes off and does something for us, then we use the type void. That's the return type. It's not a real type. It just means there is no type that we give back. It's nothingness, the void, right? So that's when we give back nothing. And that's for functions that are just meant to be called on lines by themselves. They don't give back an answer, can't be used in a larger context. They just go off and do something for us. But again, the whole point of making a function is that we can call print hello multiple times and have a bunch of hellos printed. We're abstracting away that process. So that's the goal, all right? So let's make this function, and it's going to be a void return type because it doesn't return anything. It just goes off and does something for us. All right, so I want to make a function called print hello that I can call a bunch of times. Print hello, print hello, print hello 3 times maybe, okay? So let's make that function. So its return type is void, does nothing, gives nothing back. It just does something, sorry. And it takes no parameters because you just call it with nothing and it like does the thing. And so what do we want to have happen every time we run the body of print hello? Every time we jump up here when we're called? Just like, I don't know, see out hello. Something like that. Or an indel. However you want to do it. Okay? So that's what it means to print hello. It's a void function. Just you call it on a line by itself. It goes off. Once you call it, it jumps up. Here, let's see if I can split screen that again. It jumps up here. The second I call this, it jumps up to the body and it's like, all right, start running. Jumps up here again, starts running 3 times. See that? So that's a different kind of function. It doesn't give anything back. It's going to go off and do something for us. It's a void return type. Any questions about that? It's slightly different. All right. So now that we've seen how to make our own functions, let me show you. Let's go back to this slide. Like I gave you this slide when we were first learning about library functions. Now we kind of have some more context behind it all. So when you call a function, here's what happens. Right? You say its name. It's like it's a magic spell. And so you say add. That's the first thing when you make a function call. You got to say its name somewhere. And then you have to give exactly as many arguments as it was expecting. So like add took 2 things. When you give both of them, those are our arguments to our function. 2. Most of our functions give back values. So like add, it returns something. If your function returns something, you better use that value. Otherwise, it was pointless to call the function. So get the value back with your like use an assignment or just immediately print it out. Like do something with the return value if there is one. Some functions just print stuff, right? And or just do stuff, and there is no return. So that's an optional thing. And then finally, this is the cool new idea that we couldn't understand before. In the definition of the function, there were parameters, right? These are the values. These are the parameters to this function. The int x, int y. When we're defining the function, we're working with variables because the user gave us something. We just got to do something with those things. when you call your function, you're giving concrete values. Like you're giving 42 and 43, or you're giving variable values. So what's going to go on is like the second you call the function, it's going to jump up to the definition, right? And so here's like the definition: int add, int x, int y, and then it had the body, dot dot dot. What happens is these are called your parameters, and I mix this up all the time, so don't worry if you do too. The definition is where the parameters are, and then in the call is where the arguments are. Right? Those are your arguments to your function, like you're shouting at it. Work with these things, please. So the parameters in the definition, the second you call a function, they're going to get linked to, they're going to receive the arguments from the call. All right, so we're going to jump up, once we call add with a and b, we're going to jump up to the body of add, and we're going to set x to a and y to b. Does that make sense? A is going to be shoved into x and b is going to be shoved into y. That's what it means to call the function with those particular arguments. All right, going to be passed along and get set into those parameters. All right, so that's step 4 really, that process. Are there any questions about that? So that's the idea, and it's different every time. Every time you call add again, it's going to be passing along different arguments. So the second I say add with 1 and 7, so x is now going to get set to 1, and y is going to get set to the 7 that I pass along. It's going to work with those. That's completely different to this other call, right? That's the whole point of having variables up there. You can do different things with different values. That's the beauty of functions. Any questions about any of that? All right, this is new and cool, I hope. What else? So I have a question for you. Put in the written nice page, right? Why not? Written nice page. One day I will change that wording. Well, let's go to the written nice page. I'll stop attendance after we're done with this question, so please do that if you have not. Let's go to this page. I will clear it out for us. And you can work as a group if you'd like, but here is code. There is something horribly wrong with it, but it's very subtle. All right, so here's some code. It's a function called 5. I'm calling my function, I'm multiplying it by 2, and then I'm done. You can assume like IOStream is there, like that's not the problem. Assume everything up here is what should be there. But there's something wrong with this code. See if you can figure it out. Or just put your best guess in the written nice page. So take a few minutes to discuss. You can type it up, try it if you want. But try to run it in your mind first. There's something wrong here. See if you can figure it out. Help each other. About like 2 more minutes to discuss and think about it. And the goal, right, was to print 10 in main. The goal was to print 10, right? It's trying to multiply it by 2. I have not stopped the attendance, so go do it right now. And then I will stop it in a minute. Alright, I got 20 more seconds on my timer. Get some good thoughts in there. Did we all see it? Did we all try it? Get a compiler error maybe? But yeah, this is interesting. Alright, thank you to the brave souls who posted something. Let's see what we're thinking. Nice. There's an issue with returning. 5 should have returned a number that can be multiplied, but it's a void, right? It's a void function. It's just doing something. It's printing 5. It's not like giving 5 back to be used in a larger place. So 5 just couts a 5. It doesn't like give back that int 5. Good, good, good. So it does not return an integer, so it will produce an error. Awesome, awesome, awesome. So yeah, that should have been like print 5. Then you couldn't have messed up, right? That is the point. So no returning. We're forgetting to return. We're just printing instead. So there is a difference there. All right. Awesome. So great, great thoughts there. I'll stop attendance in just a second. So yeah, what should have happened is we should have returned 5. So let's see here. Watch what will happen if we run this code, though. Let's just pretend. It might not even compile, but let's try. Dun, dun, dun. Make a new file called, where was I? Let's call it ice.cpp. Oh gosh. Ice.cpp. Boop. Boop. And of course, there is an issue with copying and pasting from PowerPoint. It replaces every space character with a character that is not space, which is weird. But let's see if I can find and replace that. So replace whatever that just was with normal space, please. Makes no sense. All right, let's compile this. G++ ice.cpp-o ice. Will it even compile is the main question. I don't think so. So it's like you're trying to multiply the result of 5 by 2, and, well, 5, it's very nice and color-coded too, isn't it? 5 returns nothing. You're getting back nothing, emptiness, from this result, and then you're trying to multiply nothingness by 2. It's like, I don't know what you're trying to do there, dude. So hopefully we see the error. This function printed 5, it should have returned 5. So if this was allowed to compile, this is what would have happened, right? It's going to be like, first of all, this function just prints 5. Just prints 5. It's the number 5 in a new line to the screen. And so like if we were allowed to like have this compile, here's what the terminal output would look like. It's like cout result of 5 times 2. So it's like, all right, I need to multiply this result by 2. So let me go off and compute it. And so it'll start running this body. And it's like 5. All right, I'm printing 5 to the screen. So it's definitely going to do that. And then it tries to multiply the nothing that it gets back because it's void by 2. And it's like, then I'll print a question mark. I don't know what nothing times 2 is. So if it could have run, that's what it would have done. It would have printed 5 and then tried to multiply nothing by 2. So do we all see the problem? Good. So this function is very different from the function that it probably should have been. It's a function called 5 still, but it gives back an int by returning it. That's the only way to give something back. You return from a function. Return the number 5. Okay? So there's a big difference between printing and returning, and this is like one of the most common errors that I see among CSCI 40 students. So hopefully I've shown you it once, and it'll be harder to make this happen now. But it just happens. It's a common error. You think that printing is returning, and it is not that. Okay? So just keep that in mind. Let's see. And I do want to spend some more time on this. This is a very common problem, right? Common error that I see among students. So return versus print. There is a difference. It's very subtle. It's all about how you use the function. Think about it in terms of how you will use this function. So like, what's the difference between add and print hello? Think of it in terms of how you can use those things in main. Okay? So let's see. How do I want to do it? Add, for example. How can I use add in main? I'm going to like it gives back an answer that sums together two values. So it's like I can call add 3 and 4, and it's going to get and make 7 for me, right? So each call to add gets replaced with its return value. Every function that returns something, you can imagine that it's going to be replaced with that thing that it returns. Like you can pretend that add 3, 4 will like be 7 one way or another. This will become 7. And then you can do stuff with that 7. You'd be like plus 2, do math, and then like put it into a variable int c equals that thing plus 2. So that's one way you could use add. Or you could like put it in a cout statement, because add called with some stuff is going to get replaced with a number, right? It's going to return something. You get to assume, and it will end up happening, that add 5, 6, after it runs the body and gives back its answer, returns that int, it will really give back 11 so that it can print 11. Does that make sense? That's the idea. What you can't do with add is call it by itself. It makes no sense to say add 2, 3, does it? Because that just computes 5, but you don't do anything. It's like you said 5 semicolon. Do you see that? That makes no sense at all. So add can't be just called by itself. It's as if you said 5 semicolon. Silly. Now you got to use it in a bigger place, in a larger context. So that's how you can use add. Print hello is kind of the opposite. You are forced to call print hello on a line by itself because it gives back nothing. It just goes off, runs its body, gets replaced with nothingness. And so it makes no sense to be like cout the result of print hello, because it's not giving anything back. Print hello by itself is going to go off and do the printing. You don't need to print its result too, because there is nothing to print. It's like C++ computes this, it goes off and it prints it. Prints hello by calling this function, tries to get a value back, and it's like, question mark? What am I about to cout now? Because it's not getting replaced with anything. So you can't do that. Does that make sense? They're kind of opposites of each other. You're forced to use add in a bigger place, not on a line by itself. And then you're forced to use print hello on a line by itself, not in a bigger place, not in a bigger context. All right? So that's that. Let me make a file that just says all that for fun. Then I promise to stop this. All right. So I'll call this return versus print.cpp. Okay, so let's steal most of this. Let's steal our add and steal our int add and steal our print hello. And so here I had my 4, 5, all that fun stuff, and a few print hellos. So here's how you're supposed to use those things, right? So yeah, add 4, 5. I can even like multiply this by 2 if I wanted to. Totally works because it's giving back a value. It's happy, all right? So those are the ways you can do it. Return versus print. And it will all be happy. 18 hello. And here's what you can't do. You can't say cout the result of the print hello call. That doesn't make any sense. I hope we see that. It's like it gives back nothing. It's going to go off and print hello for you. You're going to get a bunch of errors because like cout's like I have no clue how to print void. That's essentially what it's saying in a very long way. So can't do that. And then you also can't do this. Well, I mean you can, but it makes no sense. It's just going to like make the computer work for no good reasons. Like if you wanted to make your computer a space heater, you could do this. It's not doing anything. It's just computing stuff. It's just using energy for no good reason. So this line contributed nothing. It's going to go off and compute 9, sure, it gets it back, but it's as if I said 9 semicolon. This is like saying 9 semicolons. Like, okay, cool. What do you want to do with that 9, though? Do you want to print it? Do you want to multiply it, put it in a variable? That's the whole point. Okay? Any questions about the difference between a function that returns something and a function that returns nothing? It's meant to be called alone. So hopefully me shouting about this for a while will cause it to make more sense. Again, it happens. If you end up with a compiler error that makes no sense, check your printing versus returning. All right. Yeah, if we're happy with that, I just want to show you some examples of functions, like why we might use them. Notice how they're making main nice and small we're putting more work up here in those separate functions. That's easier for us as humans to think about. So let's talk about just solving problems, because now we have functions and we can solve more complicated problems because we can break them down into separate functions, right? So let's say I give you this problem. It's like I ask you to sum the squares of all the numbers from 1 to n, right? So for example, here's the problem. For example, if I say, if n was 3, if I said solve this problem where n is 3, then you're going to go off and sum 1 squared, add that to 2 squared, add that to 3 squared. All right, so that's what you'd go off and compute. That's 1 plus 4 plus 9, which is 14. So that's a problem. What would you do? How would you think about that if I gave you that problem? Do you kind of see how you might break it down? Let's look into that. All right, so you'd be like, all right, I'm going to write an algorithm. I'm going to do this. I've just learned about functions, so maybe I'll make some functions. Here's just kind of a way to start. We're getting a little philosophical, I guess. But we're going to make an algorithm. All that means is it's just like we're going to make a recipe to solve this problem. It's a sequence of steps to solve a problem. We got a bunch of stuff going on, and we want to break it down into little bite-sized pieces that are easier to understand. Right? That is the goal of this class. I give you a big problem. You can break it down into small pieces that each make sense, and you know how to build it up from those. Right? So we'll make a bunch of little algorithms. That's the whole point. And eventually, those tiny little algorithms will be so obviously, like you know the answer to each of them, they'd be so obvious to solve that there is no issue. All right? That's the whole point. All right? So like you're going to notice like I need to solve thing A. That actually requires this thing, which itself requires this thing. And this thing takes 2 steps. So a bunch of extra functions maybe I might need. That's the whole idea. I want to teach you how to do that because I've been giving you in your labs, right? I've been giving you fix-me's so much. I've been telling you step by step exactly what to do. That's what your Zybook's been doing. Now is the time to now is the time to stop doing that, okay? Now is the time to stop using those step-by-step instructions and coming up with them yourself, all right? That's where we're going. That's how we learn computational thinking, okay? So essentially, as you're programming, this is kind of what you do. If you haven't thought about this yet, this is what you've been doing. But let's spell it out so that we can think about it at a higher level. So you have a problem, you read it, and then you have to think about its input. You got to get its input from the user somehow. It's like I need to get n for this problem, and then you go off and implement it. So there's always a concept of input and output for a problem. You got to think about that, and then we're implementing stuff. Usually it's not right the first time, so we're going to have to talk about testing now that we have bigger problems in front of us. We're going to have to test our code, debug our code, fix it until it's right, and know when we can stop, like when is it good enough. And then, usually debugging comes down to, at least at this level, comes down to a lot of cout statements, like what's the value of these variables right here, then after this line, then after this line, how are they changing, what's going on, how can I fix it, all right? So that is going to be the process. That's how we solve problems, more or less, all right, in computer science. And let's just practice with this problem, okay? So I'm asking you to solve this. So what are each of the pieces to this problem? Like there's separate chunks, separate ideas, right? What are the different pieces? I think if you stare at it long enough, you'll notice like, all right, I need to sum stuff. That's a step. That's a piece. I need to square stuff. That's another piece, right? I also need to generate all of the numbers from 1 to n. That's a third piece. You see how there's maybe 3 pieces total to this problem? They're all separate. They need to be combined in a certain way. And then next, you need to track the flow of data because what do you sum? What do you square? Those aren't the starting point, are they? You have to start with the numbers from 1 to n. So the data is going to flow from down here. You need these first. Step 1, make these numbers because then you can square them. Then you can sum those squares. Does that make sense? So need these first. So we got that. And then, all right, I made these numbers. What do I got to do next? Well, I need to sum their squares, so I better go off and square each of them. See how that's got to be step 2? Okay, now I have their squares. Now I need the final answer. That's adding them all up. Then I can do my summing process. That can be step 3. So that's the flow of data. That's like what needs to happen before what in the process. So kind of the question was talking about things maybe backwards to how you'll go and solve it. Does that make sense? So those are three separate ideas. Maybe we can break each of these into their own functions. That's a thought. But that's where we're going. All right. So we are going to solve this problem right now. So we're going to make this sum of squares program. We're going to make some functions just for practice. It's going to make sense. And to start, let's just think about what we want. Let's just imagine a perfect world. Imagine what we want. Let's pretend we have all the functions and just use them before making them for real. All right, so we're going to write a bunch of what are called stub functions before we actually write the real code, before we get to their real bodies. Okay, so let's make a function called sum squares from 1, 2. That's a stub right now. It's just a function that gives back a value so that it compiles. You're not going to solve it correctly, but let's break it down like that. Okay, this will make sense in just a second. So let's say like what do I have? I have a main function. So let's make a file called sum of squares.cdp, and I'm going to make a main function that kind of works like this: cout enter n, because we want to sum all the squares from 1 to n. So enter n, please user, get it, and then cout the result of sum of squares. Like, if only I had this function and it was called this, it would work out. Sum of squares from 1 to, I don't know, that's what we'll call it, from 1 to n. So that's kind of the first step. Imagine that you solve the problem already. Imagine that you have a function doing exactly what you want to do, and then get that set up right, then you can go off and implement it. Does that make sense? It's like wishful thinking. That's a valid programming strategy. So if only I had this function, I could just see out its result, and that has solved my entire problem, right? That's the start. And then we just break it down. We break that down further until it's so easy, the answer is just staring at us. All right? That is the goal. So off we go. Let's make a stub version of this function, right? So let's make a function called sum of squares from 1, 2. Like, I'm not sure how to do it yet. I'm going to make a stub so I can make sure everything else is working just fine, right? So here's what it's got to be called. It takes a parameter that is an int, so int n, and then it is going to give back an int as well. The sum of all the squares of whole numbers is still a whole number, so int. And then a stub function is just one that gives back some value that's the proper type, so that you can go off and check that it compiles and you can use it in a larger context correctly. So let's just, I don't know, this needs to give back an int. Let's just say return 42 right now. All right, so this is obviously incorrect, but notice that this is going to compile now. We can check that like everything else is working. It's a very common thing to do. Like, you're not done yet, but go off and make sure like it's going to compile, like I've used it in the right way. Sum of squares. All right, so now the sum of squares for every number from 1 to 10, from 1 to 100, it's always 42 right now. It's giving back 42 as an answer. But this allowed me to confirm, like, okay, everything else I'm doing is right. Now I'm ready to go off and really replace this with the real body rather than the stub body. Does that make sense? This is a valid way of implementing something from the top down. That's kind of the idea. We're working from the top down. Okay? Let's see here. Yeah, so now we're ready. Now we're ready to actually go off and write the sum of squares from 1, 2 function. So I needed all those pieces. I need to create 1 through n, square them, sum them. So the first step is to make 1 through n. I need those numbers somehow. And so the easiest way to get them all is a loop, right? So let's put a loop in sum squares from 1 to 2. And then we need to like square the numbers. Then we need to add them together. So let's continue with our wishful thinking. Let's pretend we have a square function. Pretend we have an add function. Obviously, you could just use plus, but we're going to get examples of calling our own functions today, one way or another. All right. Let's push the squaring process down to another function. Let's have it work on that. So here's how I'll implement the sum squares from 1, 2 function. I'll be like, all right, I need to enumerate all the numbers from 1 to n. So for int I equals 1, I is less than or equal to n, I plus plus. I know how to do that. And then I'm trying to sum a bunch of squares. So, all right, I need a sum variable, int I equals 0, int sum equals 0. And that's going to eventually be my answer. I'm going to fill in sum with all those squared values, add them up. So return sum will be my answer eventually. And then the work is going to be, all right, I have an I right now. I need to square that I and add it into my sum, right? So square my I, just pretend I have a square function, wishful thinking, and then I need to add that into my current sum. So sum equals itself plus square of I. Does that make sense? If only I had square. See, I'm just like, this is a smaller problem. Just send it off to me later, right? It's a cleaner function though. It's a cleaner body because of it. I don't have to do I times I. I can just say square I. It's easier for a human to read. So also for fun, let's just use our add function. Like instead of adding sum and square, just be like, let's call add sum comma square. That's a little overkill, but it's using functions still. All right. So now all we have to do is implement all the stuff that's missing. Like, all right, this needed square and add. So I know where add is. I made that already. Let's use that. Put it up here so it knows about it. And then how do you square things? We need that add function, and then we just need a square function that will complete it. It just squares the number that it's given and gives it back. All right, so let's do that. Int square. Take some number. I can call this anything. Call it z, but I'm calling it x. And what does it mean to square a number that you're given? Just return it times itself. So like you save the work of doing squaring up there, and you don't have to look at it down here. It's like, all right, it's easier to notice like, oh yes, obviously this number is being squared because we're calling a function called square. I hope that makes enough sense. And so hopefully you kind of got a taste of the process. So we broke down a problem top down. It's like, all right, I want this. Let's pretend I have it. Try to use it. Okay, that's working. All right, now let's try to implement it and pretend I have smaller pieces that I don't know how to solve yet. Like, all right, I don't know how to solve square yet, but let's just pretend I have it. Then I'll go off and think hard about how to solve it. Maybe I need to break that down further into more functions. Okay, so that's our goal, and it really is going to work. It's going to go off and do everything right. What's the sum of all the squares from 1 to, what was our example? It was 1 to 3. That was supposed to be 14. Cool. Oh, sorry. Can't think and type. So 3 is 14. Apparently, the squares of all the numbers from 1 to 14 is this. Some squares of all the numbers from 1 to 10 is that. Cool. And that seems to be working. From 1 to 4, that should be plus 16 from that other one, from 14 plus 16. That's 30. It's doing the right thing. It's going off. The second we ask for sum of squares from 1 to 2, we jump up here with n set to whatever we typed. We go off. We start enumerating all those numbers. We keep on filling up sum with the addition result of the whatever sum is and calling square. Like this will get, we will get back the value of I squared because we made that function that did just that. Any questions about any of that? This is a good example that combines everything. Good one to study, I think. But does that make enough sense? So that's kind of the process. All right. Another very common thing that you're going to want to do is main is the star of the show, right? Main is the place that your program starts. It should usually be at the top of the file. We've kind of shoved it down here, right? Because all the things that need to exist, like if we're calling sum of squares, it better exist, and we better know about it before we call it. So that's why we had to put it up here. There's a way to like promise that I'm going to define a function later. It's called a declaration of a function. Just like you can declare variables and give them values later, you can declare that functions exist and implement them later, so long as you uphold your end of the promise, right? So this is a function declaration. You just give everything but the body, and you put a semicolon. That says, hey, C++, I promise to make this function. I'm going to use it in main. I promise to give you an implementation eventually. This is a function declaration. And this is your implementation. You can put it down after main, because all main needed to know is that it existed and what it's like, what it took, what it gave back. Then it's happy, as long as it gets the implementation eventually. Now it's good. So that is a common thing that you'll see. So let's take all our functions, declare them above main, and define them below. So I'm going to move all these guys down here, boop, below main. Now I can't compile right now because it's like, what is sum squares from 1 to 2? Because it appears after. It's unhappy. But what I can do is take that function and declare it. Declare that it exists above. So the declaration of that function. All right? And now it's happy. It knows all it needs to know to call it. And then as long as we eventually give the implementation, everything will be fine. So this will compile. This will run as normal. It's a function declaration. Technically, this was the only one that we needed to declare, but let's just do the others for fun. So that's the only one we're calling in main. But why not? Let's declare that all these exist. Cool. So these are function declarations. They're our promise that we're eventually going to make them somewhere. And so now main is at the top of the program. Looks nice. And it's like, all right, if you're wondering about what this is, you can just scroll down and find it. Okay? Any questions about that? That's a declaration of a function. It's a common thing to do. Let's see here. If we are happy, let me teach you the last piece of the puzzle. So like we made this thing, we solved this problem, we checked it for some things, like is it good enough? Are we done? Let's talk about testing. Because, I mean, once you get out of CSCI 40 and you become a programmer somewhere, then you're going to be working on giant software, right? Bunches of functions all interacting with each other. How can you be confident that these things are correct? You're going to want to test them. So let's talk about how to do that. All right? How do you know that your function is correct? When can you stop? All right? Because it'd be so nice to know that our function is going to always work no matter the inputs, right? No matter what. So technically, ints are 32 bits wide. So there's only about 4 billion, give or take, of them. So like, just take a few decades, try them all, look at their output. Then you could be 100% confident that your program works. That's one way to do it. That's, of course, not feasible for every function. Maybe functions that take booleans as input. Just check it with true, check it with false. It works, cool. Sometimes you can't try every possible input value. So how do you know that it still works? How can you be confident and know? All right. So you could wait until CSCI 26. There is a way, and I'll teach you there. There is a way to prove your function correct regardless of inputs, and you don't have to try them all. But the more common thing that is done in industry anyway is to just tests, a bunch of little tests for each little thing, and those are called unit tests. All right, so let me show you how to make a bunch of those. That's the idea. So unit testing is the new concept, the last concept of the day. All right. So a unit test is where you have a small piece of your program, it's usually like a function, a small chunk that all works together, and then you write a bunch of test cases to like have that chunk go off and do stuff, and you check each case. Right? You check that each case did the right thing. Right? So you come up with a bunch of little scenarios, and you check that what you expected to happen actually happened. Okay? So let's make a new function to do this testing, and then we'll test it. All right? Let's make a factorial function. You remember what a factorial is? It's that exclamation point in math. So 5 factorial equals that. It's 5 times 4 times 3 times 2 times 1, all those things. So let's make a factorial function. What is its return type? What should it be giving back? Yeah, so factorial is defined for whole numbers. Technically, if you want to be fancy, mathematicians have defined it for non-whole numbers, but we're not going to go there. So it takes an int, right? It's going to give back 5 factorial. So that's multiplying a bunch of ints together, another int, right? Are there any parameters to your factorial function? I think I just kind of gave that away, but do you see that there's going to be a parameter to your factorial functions? Like, what do you want the factorial of? Do you want 5 factorial? Do you want 6 factorial? So there's going to be one thing that you pass along, right? And it's going to be an int. I want 5 factorial, 6 factorial, okay? And we can just call it whatever. We call it factorial and call it factorial. Just spell it out. And then, all right, that's enough to go off and write a stub and just like pretend it exists, try and use it, make sure everything's working before you go off and implement it. Okay, let's do that. Testing. All right, so okay, let's pretend we have it. Let's be like cout factorial of 3, right? Factorial of 3, or 5, whatever it's supposed to be. That's fine. Just pretend you have it, all right? So its name is factorial. It takes an int, and you call it whatever. I'll call it n. Takes some number n, and returns n factorial. And that is another whole number, so it returns that. And so a stub answer would be like, all right, the answer is 42. Something that's an int that will make it compile, just that you can check that everything else is working fine. So that's step 1 in our problem-solving process, -o testing. Sweet. So it gives back 42. All right. Everything else is right. Main is doing it correctly. It's calling the function. So let's go off and let's implement it now. All right. So, or actually, gosh, do I want to implement it now or later? This is hard because there's a good reason to do both. There's a reason to make tests before you implement it. That's a valid way of programming. And there's a way to make, then a lot of people make tests after you program it. So let's see. What do I want to do? Yeah, let's implement the thing, I think. Or do I want to? Sorry, this is an existential crisis for me. Okay, let's just implement factorial. One way or another, let's get the body there. So what does it mean to implement factorial? I need to iterate, right? I need to iterate from my number down to 1 and multiply it into some variable. It's not it's not a sum this time, it's a product. So it's like int product. And I'm going to multiply things into products. So I can't start it at 0, right? Because then it would stay 0. Let's make it 1. And then we'll be like, for int I equals, let's start it at the n. For int I equals n, I is greater than or equal to 1, I minus minus. It's counting down. So multiply it. Multiply that I now into product. Product equals itself times I. And then that's the answer, return product. Hope that makes sense. So that's kind of factorial, and it should work, I think. It is 120, I believe. And, all right, cool, it's happy, sure. What do we do now? We think it might be right. We've implemented something. Let's check ourselves by writing a bunch of test cases, all right? A test case is just some big long, it's like an if statement essentially. It's a Boolean expression, right? It compares what you expect to see, the output that you expected to see, with what you really got back, right? So remember that Boolean expression is just something that gives back true or false. It's like what you would put in an if statement. Something that gives, let me spell that nicer, gives back true or false, true/false, or results in true or false, whatever you want to say. So that's that one. And let's write some tests using if. That's the easiest way to do it. And then we're going to make our own function that is very common. We're going to make an assert function. Assert that something is true. All right? So let's make some functions for factorial. These are going to be test cases. All right? So instead of like printing the factorial of 5, let's make test cases for it. So, all right, let's call factorial on 3. All right, what should the factorial of 3 be in math? What is the factorial of 3? Somebody? Yeah, it's 6. So this better return 6. Does that make sense? That can be a test case. Check that it is in fact 6. Yeah. If it is, like, it passed the test. That's all. That's all a test case is. It's like if factorial of 3 really gave back 6, that was what we expected it to be, we'd be like, we can shout hurrah and say passed. Factorial of 3 really was 6. Give it like a little name or something. Otherwise, else, see out failed factorial 3. Didn't work. Yeah? So that's one test case. That's all. It's just like an if statement. You're comparing what you got back. Like you're calling your function. It's doing its thing. Compare it to what it should have given back. That's all it means to test something. So unit test. the factorial of 4 should be 6 times 4, so it should be 24, right? So that's the factorial of 4. That's another test. You can make as many as you want. So there are 2 tests. And if this was like, I don't know, if we messed up or if we tried to cheat, if factorial didn't return it right, if it did this or something, if it was like, I don't know, return 6, something very subtly wrong, watch what would happen in our test cases. That's the reason you write a bunch. Boop. This one passed. Ooh, so this one passed. It gave back 6, and I hard-coded that, right? So it's obviously wrong, and so that's why we needed more than one test case. So this one fails. It's right now not giving back 24. But, of course, when you implement it right, it should be doing that. So if you fixed it, if you noticed the problem and went and fixed it, now it really will be giving back those correct things. Oh, sorry, zoom window, go away. Oops. And now they both passed. All right? Any questions about that? This is how you make a test, more or less. Just compare what you got back. Remember, this is really calling your functions, giving something back. Compare it with exactly what you expected to see. Do the math on your end. All right? That's the goal. So those are test cases. So normally you don't write out a bunch of if statements because this is repetitive. We can break this down into a function call. So let's make a function, and the standard name that you'll see a lot is called assert true. All right? So we're going to make a function called assert true, and those will be our tests. We're going to translate our tests into uses of assert true instead. Because kind of notice what's the same between those 2 tests. Let's package that into one place. So here's what assert true looks like. It's called assert true, first of all. And the whole reason it's called that is like it's asserting that some Boolean condition was true. And like it passed the test if it was true, failed otherwise. So it takes some Boolean, something that becomes a Boolean. That's like our test right here. That becomes true or false. It's going to pass or fail. So it's going to take some Boolean, and then usually give it like a string to describe the test, like a description. And it just goes off and it checks that. So it's void, it prints stuff, right? So I need the string type before I forget, since I'm using it there. But here's assert true. What it's going to do is it's going to do this idea. It's like, all right, if that Boolean expression resulted in true, so if B was equal to true, right? Or you can replace this. It's just going to get replaced with what it is. So if B, that's another way to write that. If B is true, then we passed our test. And it's not called factorial of 3 anymore. It's just whatever the user gave us as the description. So let's do that. Description. See how that like packages all the same things, similarities between these 2 tests into one place? It's like, just give me a different condition and a different description. That's what we'll be testing now. So now, how do I want to do this? Sorry, it's hard to see them both. But I'm going to make, I can make tests now. I want to assert true. I'll just put it right here so you can see them both. I'll put them down there later. I want to assert true that factorial of 3 is equal to 6. That'll be true or false. That'll be passed along to B. And then my description can be like factorial of 3. You see how that will be exactly what we just wrote? It'll be translated into exactly what we just wrote once it runs the body of the assert true function. Same with this other one. Assert true that factorial of 4 is 24. Give it a name. Those are 2 tests now. It'll jump up to here. It'll pass along into B this result, true or false. And if it's true, it's meant to be passing. Like we're asserting that it should have been true. Any questions about that? So if we compile and run this, it will do the exact same thing. And they will pass. All right, so let's put these down here. It's a normal place for them. And you could do this all day long. Like, we'll make more tests with assert true. Like, we could make a test for factorial of 5. That was supposed to be, what, 120? We can make a test for that. Be like, all right, does that one pass? And eventually, like, you're like, can I stop? Is this enough? That's the question, right? So we want to be thorough with our tests. We can't test all 4 billion integers, but we can test a lot of them. The main question to ask is, do our unit tests cover that code? Does it, like, and the word for that, it's a very overloaded term. It's like, what does it mean to cover code? It better be the case that when we, like, all of our tests somehow get all of these lines to run in one way or another. That's one way that coverage is used. It's like, are we making sure that each of these lines is somehow tested in a test case, one way or another, in some combination? So check that everything is being run. Check that all lines are being hit. Oh gosh, what just happened? Cool. I don't know what that was, but that was cool. Are being hit. Check that all lines are hit. Then there's also the question of, like, is our function correct at all? Like, what are the corner cases? Should we be checking those? Check all the corner cases. Did we forget anything? Corner cases of how the user might call our function incorrectly. Like, check that all the lines are hit. So that, what does it mean that all the lines are hit? It's like, oh gosh, something weird is going on here with my PowerPoint. Whee. And I cannot erase. All right. Let's see if I can still draw at least. So what does it mean to check that all the lines are hit? Something like, check that all the if-else statements are being run. So like, if you have an if-else, you have one test that runs the if body and another test that runs the else body. That's coverage, right? If-else bodies, etc. Have, like, if you have a loop, have a test that doesn't go through the loop. Have one that skips the loop. Have one that goes through the loop like 1 time, 2 times. Those are edge cases. Corner cases, edge cases. Those are different words. But that's kind of the idea. That's what you want to do. That's how you test something and convince yourself that it's right. Then you can stop. If your tests cover the code, all the lines are being hit, all the different bodies are being hit, all the corner cases that you can possibly think of, or edge cases, those are all in there. So let's try it. What are some edge cases? Like, what are some cases that are gonna, like, what are some inputs that would cause this function to never run the body of this loop? What could I make n? That would just skip out the loop entirely. Has to do with the condition, right? What could I make n and have it skip the loop? Yeah, I could make it 0. I could pass along 0. What should be the factorial of 0? In math, it's actually defined to be 1. So that's one thing. That's a good corner case. You see that? Factorial of 0. In math, it is defined to be 1, in fact. That's something. Factorial of 1, that's another edge case. It's like it makes the, it'll make the function, it'll make the loop run its body exactly once. That's another edge case where things might go wrong. So have the loop run its body once. So loop body runs 0 times for that one. And this one will have the loop body run 1 time. The factorial of 1 is just 1 as well. Loop body runs 1 time. That's another edge case. That's good. What factorial exists for numbers greater than or equal to 0? So what happens if I call factorial on -1? You have to pretend to be like somebody evil right now. You're trying to test your code and make sure it always is going to work. What would this do if I called it on factorial of -1? Is it ever going to get, is -1 greater than or equal to 1? I guess technically it's false, so it'll skip the loop and return 1. Yeah? So factorial of -1 is not really supposed to exist. And so we shouldn't really let the user call it, or if they do, maybe we should give back some special value that says you did something very, very wrong. So this is a very good place to think about that. So do you see how when you're trying to make test cases that cover everything, that try all the bad ways of doing things, you'll come up with some weird inputs, and you'll have to decide, since you're the implementer too, what do I want the output to be when it's -1? The factorial of -1 does not exist. It's got to return a value. What do I give back? Maybe I can give back like -1 to make sure that it's out. That's going to do the right thing, right? So maybe that's what we want to have as the output. We can test against that. So obviously, that one's not going to work, but the other two miraculously work. Factorial of 0 really is 1. Whee! So there's that. Everything's working, but this factorial, sorry, I have -1. That's its name. Excuse me. So let me compile and run it one last time. But do you see how these tests are going to influence the way that we write our code? Because now this one's failing. We've just decided in our test that, oh yeah, maybe if we get a weird value of a factorial, we should give back maybe -1, just to indicate that it was a bad thing, a bad value that we were given. And so now that will let us go and update our function. Just be like, all right, if our n, factorial only works for n greater than or equal to 0. So if n is less than 0, we get a weird negative value, then the factorial doesn't exist. So like we could see out something here. We could exit and stop the program if we didn't like that a lot. But we could just return a special value, maybe ask the user to check for that, like -1 if it's an invalid factorial. And so now it's really going to give that back. And we will have passed our last test. Now they're all passing. And so we've got some tests that make the function run its loop a couple times, 3, 4 times, 0 times. We have some invalid input that we've noticed that we need to check for. Once you've done that, your tests have good coverage, we say, and you can probably stop and be confident that if you called factorial of 6, it's also going to give you back the right answer. Okay? So this is like enough for me, but if this was like mission critical, we're working on the lunar lander right now software, you might need a few more tests. All right, but that's a good start to it. So this is assert true. We're making sure that this is true. We're asserting that this better have given back true. We're checking what we got with what we expected to see. All right? Yay. Any questions about any of that? That was a lot. All right. I have questions for you now. Oops. Ah. Shield your eyes. How dare I forget to... Whee. Oh, no, this is... Never mind. This is PowerPoint. This is stuff I wrote on a previous slide. So, okay, PowerPoint is broken. Let me restart it. The suspense. But I've made a function that is incorrect again, and so I'd like you to write a test case for that function. You don't have to write it down anywhere, just like on your own piece of paper, on the server somewhere, give it a try. But eventually I will show it to you. My PowerPoint does not want to load right now. Can you give me a better computer? It's trying so hard. Yay, and I sure hope everything else got saved. Aw, man, they didn't. Alright, let's see what I was trying to say here. Sorry about that. That is very unfortunate. So that didn't get saved. What else did not get saved? I guess that's where it stopped working. So, I'm sorry, I wanted to give you these notes, and then we lost them all. Check that all lines are hit, I think is what I said. Are hit. And then, now my pen is weird. Gosh. Everything's going wrong. And this was like your if-else bodies. I think that's what I said. Loop bodies, etc. What else? What else? Check your corner cases. I think that's also what I said. Check corner cases. And edge cases. I hope that it will save this time. But here's the question for you now. Here's a function. It's called square. We made our own square function, right? Already. But there's something wrong with this one. So see if you can write a test case with the assert true function. Here's the top of the assert true function. Here's what it takes. Boop. Let's put it here. You don't have to write this down anywhere that I can see it, but for yourself, see if you can come up with, like, what could I call square with to show that there is an error here. First, notice the error, I guess. And then try to write an assert true statement, an assert true call, to notice the error. Like, compare what you got back with what it really should have been. It's not going to be the right thing this time. All right? So see if you can try that. Take a couple minutes, stare deeply into this function, and see if you can figure out the issue, and then how to notice the issue with a test case. All right? Any questions about the question? All right, so give that a try. I'll give you a couple minutes to think about it. But see if you can notice the error, and use assert true to write a test that will fail. Write a test that's going to fail, and it will very subtle. All right. So, did anybody see a problem? Any brave souls would like to share the problem that they found? Did we not find it? So, all right, let's run this code. Let's try to square some numbers. I'm going to call square on 1. Pass along 1. It's going to compute. It's going to return x, which was the original value. 1 squared is 1. So that one works. Do you see the error now? If I call square 2, what's it going to return? It's going to return 2. Good. So the issue was it wasn't even using the squared number variable. They're just returning the original input. And so there's only one value, or I guess, yeah. There's only one value that works out, I think. And so that's not good. Square of 2 should have been 4. So that's a test that we can write to make sure somebody fixes this. So we can assert true. And again, you should not be doing it this way. You should be like using some special close to checker, but I'm just going to write it out for fun. Assert true square, because this is a double, right? It's returning doubles. Square of 2 should be equal to 4, but again, you should never do it this way. Check that it's just close to 4. And just give it some name now. Test 1 or something. So that's my first test, and this will, if we fix it, it will compute square of 2, and hopefully it's going to give back 4 this time. That's the goal. All right, do we see how that's a good test that's going to fail right now with the current implementation? Are there any questions about that one? That's one issue. Solved. All right, let's say we solved it. We got that test to pass. Here we go. Here's a new version. It's still wrong. Take another minute to try and notice the error and write a test case for that one. See if you notice it this time. There's still something wrong. All right. Did anybody see the problem? What's the issue? Still something wrong. Is it too subtle, or it's just we're too worried about the midterm to talk right now? That's fair. So, all right, this is supposed to be square, right? It's supposed to square numbers. It's going to work now. Square on 2, if I can spell square. Square on 2 is going to give back 4. It's going to work. But the issue is types. Really, it's not square at 2. It's square at 2.0. Yeah, this is a double I'm being given. It's a double I'm returning. So it's meant to square doubles. So this is square of 2.0, which is 4. And that does check out. That works. But what's going to happen if I ask to square 2.5? Alright, so it makes the squared num variable, and that's what it returns. It converts it to a double, but it's an int. It's declared to be an int. So squared num, num is going to chop off the decimal places. So like we're trying to put 2.5 squared, which I have forgotten what that actually is. Python 2.5 times 2.5 is 6.25. That's what it should be. We're trying to put 6.25 into here, and it's getting all of its decimal places chopped off. So squared num holds 6, and it will return 6. That's not what we wanted. Do we see the problem now? Fun with types. So let's write a test to make sure that this gets solved. Right? Assert true. Somebody better fix this, because this test will fail right now. Asking to compute square of 2.5, and it should be, right? It's always compare it to what it should be. Check that it's right. It should be 6.25. And again, you shouldn't be doing it this way. You should be using like absolute value, making sure it's very close, because these are doubles. But it will probably work this time. Test, give it another name, test 2, let's say. But again, we're comparing what we actually got. We're really calling the function is getting replaced with what it's giving back. And we're comparing what we got with what we expected to see. That's what it should have been. Right? And that's what makes a test. Any questions about that? And then hopefully once somebody fixes this one, it will be a fully correct square function. Are we good with that? So yeah, we've come so far today. We've made functions and we've tested them. Very fun, I think. So if we're happy, let me release to you your next lab. Why not? If you'd like to get started on it early, you can. But I know we have the midterm, so it's going to be due a while from now, week 8. But here's the write-up. Longest words and vectors. So this is a vector / array kind of lab. So first of all, what I would like to say is that for this lab, starting from this lab onwards, you guys can work in pairs if you would like. If you'd like to work together with somebody, I will allow that. You now know enough of C++ that I trust that you'll learn all that you need to know. So I don't think I'm going to take away that privilege, so just assume that unless I say otherwise, you can work in pairs from now on. I do want each of you, pairs of 2 though, can't make any larger groups than that. Each of you should all submit separately to the autograder so that it's just easier for me to give you a grade that way. It's just automatically placed into your grade. So submit your codes, your identical codes separately to the autograder once you're finished, but please also include a comment in your code talking about who you worked with so that when I see identical code, I don't, like, red flags don't go off in my brain, okay? If you are not sure about how to, like, efficiently share code between you and your partner, I can show you some ideas that I have, but I also trust you to figure it out if you would like. And then, yeah, if you would like a partner, feel free to post on Discord if you'd like to search for one, or just like walk around the class. If you can't find one but you want a partner, then I can like start a list of people and just pair you off as the list grows. That is one way to do it, but that's the first thing. You're allowed to work in pairs from now on. If you would like to, it's not required, but you can. And then let's go to the code. Where do I want to be? Code 40 lab. What is this? Lab 4. So here, if it loads, are all the files for Lab 4. 2 CPP files and 1 file that contains the entire works of Shakespeare. So this will be fun. Alright, so here are your files, and the first thing I want you to do is write a program that calculates the longest word in a file. It's really cool. So you're going to find the longest word in a file, and you're going to give it to the program as if you typed it all out. You're going to give it to C, and you're going to redirect it. You're going to use the less than sign. I'll show you that in a second. So just pretend that the file is being typed, and you're just going to get every word through CN, and here's how you do it. So you're going to keep track of which word is the biggest. Like, you're going to get a word, you're going to read that in, and figure out, like, you need to make a new variable, which word in this thing, and all these words that I'm being given through CN, which one is the longest. So you have to keep track of that. It's like a maximum problem, okay? So there's some weird code that I gave you, and it's a cool little trick that just keeps reading words until the file's over. So the way you do it is you just say while, and then you put as the condition of your loop a CN statement. It's so weird. What this does is it runs CN, and it gives back true or false depending on if it just read another word successfully. Because at the end of the file, it will have no more words left. So this will fail, which is kind of cool. So if you put this in a while loop, it will get a new value for current word, and it will return true if it was successfully read. So in the body, you are guaranteed to have a new valid word read from the file. It's kind of cool. So just keep it like that. Just pretend you have a new word called current word in the loop. So this will be running millions of times for all of Shakespeare's text, okay? And for every file that you write. So yeah, just the while loop is going to get a single word from CN and place it into the current word variable. You can assume once you hit the body that you've just got a successful word read from the file, the next one, okay? I hope that makes enough sense. When you try it, it should be okay, okay? So that's that, and then you'll just keep track of, like, this was the next word. Was it the biggest one? Then I get another one. Was that the biggest one? You're going to have to save it somehow, and then just output that the longest word was that, all right? So the way, you'll compile it normally, but the way that you give an entire file to a program as input to CN is you run it, and then you give a less than sign. It's like a little arrow on the terminal. It just means take this entire file and type it. Essentially, the terminal is going to type the whole file into the program for you, as if it were through CN. All right? So this is how you're going to run the program with a given file that has text inside of it. All right? So try making your own. But here is, for example, what happens if you were to run the correct answer for the program with the entire works of Shakespeare. Here's legitimately the entire works of Shakespeare, plays and sonnets. And apparently the longest word, you don't have to like clean it up or anything, it's just everything in between spaces. So it's like this big long word that includes a lot of dashes and then also a semicolon at the end. Okay? So that is apparently the longest word in that entire file and includes the semicolon. All right? So you should make some files to test it yourself that are smaller, that you know the answer to as well, but that's how you do it. Are there any questions about this program? Calculating the longest word. Just a big long loop, essentially doing a maximum style problem in a certain way. All right. If we're good with that one, your other problem is this program on vectors. So here's what we're going to do. This one is going to get us practice with vectors and command line arguments, and then loops and like iterating and stuff like that. So for this file, you're going to get as input a bunch of numbers as command line arguments. So the user is going to run your program, your vector operations program, and you're going to space separate all the numbers that you would like to put into a vector in that order. So this will put 1, 2, 3 into a vector if you run it like this. This will put 2, 5, 4, 0, 3 into a vector if you run it like that. All right? And it will make those vectors. Does that make sense? And then your job in this program is to like build up a vector with these values and then keep track of the min, the max, the index of the min, the index of the max, and then the second smallest element and the second largest element. So if you run it like this, this will make the vector 1, 2, 3 in that order. So the min value is, of course, 1. The max value is, of course, 3. The index of the min is 0, right? It's the first thing. The index of the max is 2. It's the index 2 thing. And then the second smallest and second largest element are both 2. Does that make sense? So that's fun. Your vector might be out of order, though. So here's this one. If you run it like this, you'll make a vector holding 2, 5, 4, 0, 3 in that order. And so the minimum is 0, which lives at index 0, 1, 2, 3 this time. And then the maximum is 5, living at index 1. Does that make sense? Now the second smallest element is the one after 0, so 2. And then the second largest element is the one before 5, so 4. You'll have to go and find this. Any questions about the output? What's happening? You're building up a vector out of command line arguments, right? So you're taking, here's argc and argv. You are going to go through all of the argv from index 1 onwards, right? Because that's all the numbers. You're being given a bunch of numbers, and they're being given to you as C strings. So you better use A2I or S2I to convert those, because you're going to make a vector of ints, right? Not a vector of strings. You're going to need number stuff. So you need to do that conversion. And then once you've done that, you've read all those command line arguments, not including the program name, into the vector v, you must go through that vector and somehow find the min element and its index, find the max element and its index, and the second smallest element and the second largest element. All right. Duplicates will count as separate elements. All right. So if you had the vector 1, 2, 2, the second smallest element and the second largest element is still 2. It's the middle thing. Just start chopping off, essentially. Duplicates count as separate things. You don't have to, like, merge them all into one thing. That'll make it easier on your end anyway. All right? So second smallest and second largest, I don't care about their index, just print their value, which actually is a little bit of a hint at the same time. All right? So that is that. Yeah, I've given you a hint if you read the comments. So if you read them carefully. Any questions about this? So you're taking command line arguments. They're a bunch of strings. You're building up a vector of ints, because you're getting a bunch of space-separated numbers. And then you're doing stuff with that vector. Everything is being inserted in that order, so you're pushing back to it. And then you're finding indices and maxes and mins and things. Right? Any questions about that one? So that's the harder of the two, definitely. So get that working. Compile in the normal way. And that is your assignment. So you're turning in those 2 CPP files. You don't have to turn in Shakespeare. I have my own copy of that. So yeah, turn in those 2 files, and that'll be it. You're gonna get more points for vector operations, since that's definitely the harder of the two. All right, so that's your lab 4. Do week 8, and you can work in pairs. Any questions about any of all those words that I just said? All right, so I think that is the end where I want to stop in the slides. We've got our lab. All we have left is the midterm on Thursday, so don't forget about that. You'll just come here and you'll click this on Canvas to start taking it. Okay? So I think that's everything. The rest of the time is all yours to work.